Okay. For example, if you don't ask something like this, you will after I demonstrate this, but generally you don't. When you draw a beam, you do it like this, right? And when, in my class, when I start with this, and then the next page, I forget, I do this. Can I do that? It's just a triangle in a circle, right? So can I switch it? Can I draw it like this? Can I draw it like that? Which one is no? I give you something to refer to. I say A, B, C, and D. Which one is the no? B and C is what? Think about it. Think about it. This is a symbol that has been given to you since the day of statics, and yet you never question it. It's just a triangle, but you don't question things like that. Can I draw the, with the equal sign? Can I draw the, I don't remember the English word. Can I draw a triangle like this? No, please don't ask something like that. All right. So if you don't ask, I'm just gonna pretend I never mentioned this, right? And now you get to carry your questions back home the way you wish, because you don't ask questions, right? You need to ask a lot of questions because this is your time. When you move on from this class, the next class, or when you graduate, and you don't ask questions, you come back, you're gonna ask me. I'm gonna say, hey, I'm gonna charge you, right? For the consultant fee, something like that. Just kidding. Anyway, let us go back here. Let's forget about it. It's a distraction because you don't ask, so it's gone. Okay. So now let me repeat what your friend has asked. First and foremost, yeah, because something like this, it can lead to some misunderstanding at times. Yes, you're right. The beam should really look like this in the drawings, but I'm too lazy to draw two lines for one beam. It's such a headache. So I use one line. So you need to forgive me for that. But now you understand, okay, one line represents a beam. Okay? And it is actually you in the real world who need to first figure out the load that your floor system will have to carry. And second, come up with the system itself. So this is your job to determine how many beams you actually want to put on. You can ask me, hey, now I put one beam here in the middle to split the floor. Can I put two? Can I put three? What's going to happen? Let's say if instead of having one beam here, I add two more. Question is, can I do that? Yes or no? Please participate. There's nothing wrong with it. Yes, you can. So what's going to happen if you add more beams? Think about it. What's going to happen? What's going to happen if I break this? I have to pay for it, right? What's going to happen if we add more beams? One obvious thing that you should see is that I need to see your face. Yeah, you guys are blurred, if I don't wear glasses. One first thing that's going to happen is that your floor becomes shortened, right? So you can select the lighter floor system. So it's a good choice when you have a very heavy load like this. Look at the number, it's pretty big. So if you use, say, not a lot of beams, the floor will become large and thick and heavy, and your beam will therefore carry more weight and more moment. there will be a time when, wow, the beam is, we cannot, build the bigger beam than this due to some limitations. So this becomes a solution, add more beams so that the beams and the floors become smaller. But you're going to have to like juggle to obtain the most optimal design, because yes, when you have more beams, the floor becomes smaller, but you have more point load on this beam. So that's a trade-off. So this is the fun that we can have when we try to design something that has never been built before. It's our free world, and enjoy it, because that's just about the only freedom you can have. Because after that, it's all calculation based on the standards and the rules and so on and so. Okay. Now in your, you can say it's your own baby. You create this. Okay. So let's what do I do? Let me erase this. Oops. Why? Okay. There's a delay. So now, I think you may have a little problem understanding this, so I expect you to ask questions. Okay. You can see B2 itself. I think I'm going to have to erase something because I draw too many lines so that you can't see B2. Okay. This B2, it has no columns to support it. So the support for B2 has to come from the cantilever portion of this beam. It goes out to support B2. It's your job to make sure that this beam, B3, we have to extend its arm out and support B2. Because otherwise, you're going to have to use balloons to support B2, right? We can't do that. So we have, as engineers, need to provide support for B2. So now you have here support for B2. Next, your beam has to have at least 2 support, right? Otherwise, it has to be a fixed support. But generally, we don't have fixed support unless we have a very strong system that can act exactly like this. So we don't. So we need to provide another support for B2. That's going to come from this beam, right? It has to extend out and give the support for B2. So now you see B2 has 2 supports. It should be said. Correct? I need to erase this as well. Any questions? So B2 seems to be safe, but there's one tiny little thing that you guys need to know. I have been told this when I was a junior engineer in the company. And I think it's a good idea that you know it now. Because we have, KUTT graduates, just a good reputation going now, Can you tell your friend to just stay strong, man? Don't dream about something. Dream structure now. You drag yourself here, so just stay a little stronger until your lunch, okay? Yeah, that's what I love doing. That's why I love classroom. Because I can do that. I cannot do that to folks at home, right? I like the fact that you try to be here in the classroom. You dedicate yourself to your education. You want to be here, but then you are tired because last night you played game too much. That's understandable because it's teenagers thing, right? You guys need to have activities, good or bad, I don't care. But when you decide that even you have had your activities all night long, you can bring yourself here. So that is admirable. And when you are here, just hang in there. All right. You know, I used to be like that. I brought myself to the classroom. Then I fell asleep badly, waking up with my hair, with the drooling all over the place. And then the next hour, I told myself, wow, actually sleeping outside the classroom is more comfortable. So I start skipping the class. There's no one to scream at me like that, you know. I was just taking a long sleep until the class was over. So then, you know, stupid or smart, you realize that actually sleeping in bed is much more comfortable, right? So I start skipping class. So I admire your courage, but your friend has to help you out, you know, trying to give him some little reminder. You need something to drink, you know, or maybe you can drink anything except some maybe alcoholic beverages, you know. No beer, no whiskey, please. Okay. Anyway, where were we? Okay. Here, just look at this. The question that you cannot answer right now is, what about this corner? What's going to happen to this corner? Who's going to support who? Because if you can see that for your B2, you have two supports here. So that means B2 will survive. When you look at this beam on the vertical direction, it has to have the support coming out of this beam as well, coming out of this beam. Right? So the cantilever portion here, this cantilever portion will provide the support for this beam. Comes the support for this beam. So now this beam has two support as well, so it's safe. So whatever happens at the corner, let me tell you right away, because you're just gonna start, you're just gonna stare at the picture like that. They need to support itself. Nobody is supporting anybody at the corner. You as engineers must make sure that this portion is strong enough to stand by itself. Say, supports itself. Maybe I can say that. And this too supports itself. So when you draw the free body diagram of the beam, somebody's taking notes, so let's slow down a little bit. You wish to say something? It's a lot of fun, right? Yeah, kind of. Yeah. Right. Yeah, for me, there's no place I enjoy more than being in the classroom as well. Anyway, you ready? So some of your friends still taking notes. So I'll wait for the proportion to stop. Please, if you don't understand, if you wish me to repeat anything, do let me know, okay? Don't be shy. Especially some guys say, you know, you don't speak because your English is not up to the scratch. But remember, in the next 2 years' time, you're gonna have to take that damn IELTS exam anyway. So in fact, you can practice your English with me for free, right? But such is a human nature. You don't like to practice for free. You're gonna have to pay someone to talk English too. That's a sad thing, right? Yeah, take a lot of notes. Take a lot of notes. Yes. And if you're curious about anything, ask me, because your question may open your and your friend's world a lot. All right. So if you are drawing maybe some kitty cat or Captain America, I think I'm ready to move on. All right. So I can now draw the free body diagram of the beam B2. Okay. What's gonna look like? I will try to stay on this page so that you can get the feeling. B2, in order to give you a feeling, I will use the green color. So B2 is going to look like that. All right. So maybe to make things more clear, I can call that point A and call that point B. So that becomes point A and that becomes point B. If you like to draw a circle before the rectangle, you can also draw this. Doesn't hurt anyone. Okay? Doesn't matter. But you can't draw two rollers. Okay? Because yeah, you'll be able to sit on the roller blade. But the thing is this. If I draw that, this is like taking you out of topic. If I draw that, but my load is like that, what's wrong? Yeah, nothing's wrong. So why can't I draw it like that? Why can't I put my beam on a rollerblade? I only have the vertical load, right? Can I do that? Can I? I like circles. I don't want to draw triangles. So may I please draw just circles? Triangles hurt me. I don't like to draw circles. I don't like to draw triangles. I just love to draw circles. So can I draw two circles? Is this what? Yeah, yeah, it has only vertical load. Do I draw anything else? So take this. You have that. So one day, a mosquito fly and hit the beam. According to Newton's law, your beam should move until eternity, right? If you don't lose energy. So just like that. That's why we can't draw circles, because we need to give equilibrium to the system, even though we don't have the load. That's just about it. We need to draw the system that is equilibrium, stable. It's not just, hey, I have just the vertical load. I draw that, I can calculate reactions, right? But it's not the same when I change one of the circles into a triangle. If I have two triangles, that's going to be more complicated. We'll talk about that at the end of this class, if I don't forget. But I don't talk about that now. If you still remember what the difference it makes between having one triangle and one circle and two triangles, ask me later. Not now, because it's a good idea to know things when the time is right. Now it's not right. Okay. All right. So now, what load does this B2 carry? It's going to carry the uniform load, correct? And you can draw it like this. That's my uniform load. Lovely. Yeah. You can draw it, you can use like that too as well. I think it's universal. Yeah, it is. But if you want to draw something like this, I don't think that's universal. No, I don't think so. Or maybe like a spring, I don't think that's universal. But that is universal. You know, please, especially in the exam, you don't spend time trying to make it absolutely beautiful so that I can give you extra credit for drawing such an impeccable uniform load. No, I don't give you extra credit for that. So it's no use, yeah, even though that looks very, very formal. And this doesn't give you extra credit either. Things like that. Okay. So yeah. So now this is your first experience taking the B2. Okay, so it's gonna look like that. So before maybe I should start the calculation right away. So we have the date load and the live load on the floor. Now everything looks messy. Let me erase this. Okay, that is the width here. You can see 1.5 meter, right? 1.5 meter. And this is the direction of your floor. What does it mean? It means that half the floor or 0.75 meter will go on to B2, correct? And then another half will go on to this blue beam, which actually is B3. Can you feel it? Half the floor will be supported by B2. Another half of this floor will be supported by this blue beam or B3. So that we can safely say this is the tributary width. Take your time, okay? And you know what? What's wrong with the first row anyway? What's wrong with the first row? Why you start sitting at the second row? What's wrong with it? Somebody die on it? Yeah, it's like that the space here is not enough, like to protect you from me, right? So you need another row. As if I fire bullets at you. Anyway. Any questions? Okay, so that means we can do a little calculation, right? Now, some students will forget this. I used to forget this because, one time I had done so much steel structure that I forgot the weight of the beam. Because in steel, the weight of the beam can be neglected. But in concrete, no. Concrete beams are heavy. So you need to consider the beam self weight as well. Right? So that means this uniform load on the beam will be how much? Can you help me calculate? B2. W is going to be the weight of the floor, correct? Which is 600 plus 1500. That's date load plus live load. Remember that the load is the load per area. We need to multiply with the tributary width, which we now know that is 0.75 meter. There, see? So this will be multiplied by 0.75. You okay? Oh man, what happens to the break? You leaving? What? Yeah, that's what I was saying. Why didn't you do it during the break, man? And he is gone during the most important process. Oh, poor thing. Okay, guys, that's the way of the flow on the beam. But we need to also add the weight of the beam here. The weight of the beam has been given, so it comes in. Look at the unit, which I already obscure. Okay, it's kilogram per meter. So that's a unit. So it can be added together because they have the same unit, right? Now be careful. Sometimes when you're dealing with the system, they can be walls. And some beams will also have to carry the wall. So you need to check with the architectural plans, okay? In this case, we don't have any beams that carry the wall, so that's great. Folks at home, you have any question? I can't see anyone at home at all because I'm sharing screen. It's kind of sad to see a lot of students. Okay. So, any question, guys? Are we crystal clear still? Oh, excellent. So, can you punch a calculator for me? I don't want to open my old notes. Oh, 2075? Oops. Sorry. Oops, that's the wrong one still. That's it. So everyone concurs. He punches the calculator correctly. I don't know why the Americans say punch the calculator. It's not a sandbag, you know. Maybe they do punch it when they have bad grades. Anyone think this is incorrect? 2075. That's not a lottery. It's a load on your beat. Hey, come on, ask me. It's like if I'm too close to the speaker behind, just gonna do the feedback thing. Any question? Are we ready to move forward? Yes, we are. Right. So yeah, we better move. So now you know this is exactly what it is. So I can move on to the next page and try to draw the beam properly. B2. What's the length? It's 4 and 2. Yeah. Okay. Yeah, 6. But you need to understand that this is 4 meters and that is 2, 0. And we have the uniform load beautifully drawn on it. That's a 2075 kilogram meter. Okay. So now, what are we waiting for? Okay. I think the picture is not on that, which means I'm losing the connection. So I need to. Okay, now it's back. All right. What are we waiting for? Simple determinate structure, right? You do call it determinate, right? You know what? You know the full name? It's called statically. Oh yes. Determinate structure. Because you can determine everything by using statics. So it's called statically determinate structure. But before you do anything, can you sketch the shear force and bending moment diagram right away without doing anything, without any calculation? Can you sketch it by just looking at the beam without doing any calculation? Use your feeling, Luke Skywalker. Use the force. Can we do it? You better be able to do it from now on. Because you've done it so many times with your head of the department, Ajahn Chulapot, right? You've done it numerous times. So I'm not going to tell you how to do it anymore. So you better know that when you see the beam like this, it doesn't matter what the calculation is. You know that your shear force diagram is going to look like this. And then your bending moment diagram is going to look like that. Correct? Yeah, and now you start feeling the blanks. How hard can it be? You can even fill in some numbers without the calculation of the reactions, correct? Can we do that? So what numbers can you fill in here without calculating the reactions? Challenging, right? You know, let some folks catch up. And what I'm about to show you is not a miracle. It's experience, which you should try to gather by doing more exercise. If you do enough, these things become automatic. It's not a miracle that I can calculate this, because I've been doing it for 30 years. I started doing this before you were born. So if I could not do it now, I better quit the job, right? And go sell noodles somewhere. Maybe I will. You know, but not now. Okay. You ready? Some you still make notes. Okay. Okay, it's a badly drawn picture. I need to make some adjustment, because you know that's the maximum positive moment better be here, right? Better draw it more beautifully, like that, and better make things a little bit more beautiful by. Okay. Yeah. Okay. And the bending moment should move. The negative moment should move a little bit. Yeah. While you draw. Why it take so long for you to draw? For me, just okay. All right. So, you know, this is 2075. I can say that the shear here is 2075 multiplied by 2, right? Can I? Can I not? Yes or no? Yes. Why? Because I can easily cut the free body diagram of this part, right? What happens when I cut the free body diagram? It's just that and that, and that, and that, right? See, nothing more. I haven't done anything that you haven't done before. It's just free body diagram and equilibrium. But I choose to cut the free body diagram of this part. And so I better have the equilibrium of that part as well. It doesn't matter where I cut. I always have to have equilibrium. Correct? So I know that that shear is 2075 multiplied by 2. Am I correct? And what about the moment? It's always 2075 multiplied by 2 square over 2. Because if this is your load, it acts here at the location 2 over 2, right? So when we draw together, it becomes, when we write together, it becomes 2 square over 2. Or I can make this into a rather simple form by, okay, that, if that's W, if that's L, so that is WL, correct? The total load is WL, X at L over 2. So your moment better be WL square over 2. This is not a miracle. This is equilibrium. Because the centroid of the uniform load doesn't act here. So that's why we need to have moment, correct? Otherwise, it's going to rotate. So you guys who still struggle with the shear force and bending moment diagram, I suggest that you practice it now. Because I come in here in this class, I assume everyone is good at this. And your knowledge is building up. Okay, so you keep learning new things and new things and new things every day. We don't go back to the stuff we have done before. Because you move forward, you don't move backward, right? So that at least the 2 numbers that I can tell you, that you can tell me, you can do it, you can have it right away. So 2 square over 2, so that's the same thing, but I better keep the format so that you know. That looks like a tree. Any question? We just yeah, 2 lines. The B2. Okay. Okay, guys. Question about this? So I think it's high time we calculate reactions, shall we? Can you do it for me? Pardon me, I need to go back up a little bit. We call that point A and B, right? Okay, so that's right. So can anyone calculate RA and RB for me? Do we need to show you how? Please, do I need to show you how? Seriously, no, right? So RA is just, RB first. RB is 2075 multiplied by 6 multiplied by 3 over 4, right? And RA is 2075 multiplied by 6. That's the total load. So that's multiplied by 1 over 4. Okay. You know, the one thing that I cannot cure is that many students would like to take the moment just once and then you know, use the sigma Fy to obtain another reaction. So the question is, what if the first one is wrong? What if somehow you punch the calculator incorrectly and get the wrong reaction? You throw away the chance to check your calculation. So for me, I always take moments twice when I was your age, just to make sure that my sigma FY is okay. So numbers, please. That's a lot. Can you just 9,000? RB? 9,300? Let's say, okay. You know, one more thing. This country, we kind of like the kilogram force unit. Okay. So in fact, I can call it this kilogram force, because kilogram itself is mass. It's not a force. But somehow we use it as a force. So what? We call it kilogram force. Okay. And it's not just about this country. Many countries use a kilogram force unit. And RA? You can just say the number. 3112. Okay. Okay. Let's hope that our sigma FY is okay, right? You know, sometimes very, very rare, students would take moments for both reactions like this, but then they don't check sigma FY. You know, I almost, hit my head at the wall because it's just so sad. Oh. Anyway, so we now know that's 3112. Right? And how much? That is 9338, right? The height is the reaction, not the shear. So now you can calculate the distance where the maximum moment is. That's the distance where the shear becomes 0, right? So that distance x is equal to 3112 divided by 2075, right? So who doesn't know how this comes about? We all know that, right? One something, 1.5 maybe. Come on, we need to take a break soon. Give me the number. 1.5 something maybe. So you're the only one who can help me out. That's 1.5. Okay. Okay. Round up, right? Pesticide? No, it's not pesticide. I don't know what it's called. Anyway, so with that in mind, with the distance where the shear becomes 0 is known, you can use the area of the shear force diagram to calculate maximum positive moment, right? You know that? Yes, good, excellent. So I can maybe use different colors. Yeah, and so that area is equal to a half of 1.5 multiplied by 3112. Okay. So this is like the review of the material. So you can easily obtain the maximum positive moment. You can easily obtain the maximum negative moment. But you better be able to do this as well in the future. For now, this location. the location where moment becomes zero. We call that point of inflection. Do you know that point? Do you know? You don't? So you never asked to calculate that? It's fine, it's fine. Just you don't know, you don't. It's a point where moment changes the value from negative to positive or vice versa. It's important because that point moment is zero. It's a point, if you choose to connect the structure, will be the point that you can do it very easily because you don't need to make sure that at the connecting point, you need to transfer moment. It's called point of inflection. May I, you guys catching up? Tell me, because I will carry on. Or should I wait? So some wind coming off here, so my hands could be here. My hand. So can I go on for a few more minutes, or you guys need catching up? Wow, left-handed, nice, but not nice with this kind of desk, right? So okay. First, this point is rather important. And if you, are you ready? Are you ready? Okay, now, some of you still making notes. I want you to just, listen without writing anything. Okay, so you're just ready to write something. I thought you were writing something. So please take a look at this. You have calculated the deflection of the beam before, right? But are you aware that when you look at the beam, you can actually tell or guess how your beam is going to deform or deflect? And when you look at this kind of load, this is the overhanging portion, correct? So when your beam is going to deflect here, how should it deflect? It has to come down like this. Hope you can see, here, like that. Or I can draw the line. It should deform like this. Color is not contrast enough. Let me use a different color. Maybe green will do the job. Because you have a support there. So your beam will deform like that. Or like this. Am I correct? That's how you don't think about any calculation. Just use your feeling. Any kids without the engineering knowledge can imagine that. Okay? Just imagine. You can bring your plastic ruler up, your finger here, and try to bend it. It's gonna have to deform like that. Right? And when you fix this, and you try to deform this portion will have to deform like this. It has to come down like that. Right? So it is this. So do you realize that this is what we call the positive curvature in your bending moment diagram, correct? So the sign is positive sign, and we call it positive curvature. This is what we call a negative curvature. It's a sign convention for your negative bending moment diagram. So please don't take any notes yet. Without doing anything, you just take a look at your beam and you realize that it has to deform like that. It has to deflect like that. You must realize right away that this beam will have both positive and negative moment just by looking at how it is going to form. No calculation needed. Just use your feeling. Talk to the structure. Right? But it doesn't talk back. So you have to just like talk to yourself. You better know it. You better feel the structure. Okay? So before we take a break, one more thing. Please don't take any notes. You know you have a positive curvature somewhere because your beam has to deflect like that. You know you have a negative curvature somewhere because your beam has to deflect like that. So your beam has two curvatures. So somewhere there will be the place or the location where the curvature will change from positive to negative or negative to positive. And that point, ladies and gentlemen, is the point of inflection. Because before it changes the curvature, it means that it has to be zero first, right? So that's it for the break. Okay? Any questions? You know, I can see the classroom, and I know that's what's been missing for folks at home. You can talk to your friends in the class. Yes. Point of inflection. Inflection. Yeah, here. It's the same point. It's a point where the curvature changes from negative to positive or vice versa. So that means it's a point where moment becomes zero, right? That's it. Okay. Pretty like piece of cake, right? Yeah, it is not heavy. So he's ready to take a break. So, okay, we can have a 15-minute break, right? You need a longer break to recharge your battery now. So folks at home, any question? I suppose not. See, you can talk to your friends in the class. That's why the performance of some of your friends are down, because there is no one to to discuss with when you're at home. And when you cannot catch up with the class, you're just lost. Okay, so stop the record.